Good morning, everyone. Welcome to this webinar hosted by Rockflow Dynamics. My name is Joanne from RFD's Aberdeen office, and today I am hosting with my colleague Serkan, who is in Hamburg, and my colleague Alexandra, who is in Aberdeen as well. So this is the third part of our new energy webinar series and the final episode in this series. So if you missed the last two webinars, you can see the geothermal one and last week's webinar, which was exploring new technologies for integrated asset modelling with CCS on our YouTube channel. Today, Serkan is going to be showcasing an overview of the reservoir modelling tools that we have within tNavigator to effectively model CCS projects using integrated workflows, including reservoir characterisation, petrophysical modelling, EOS, geomechanics, and uncertainty quantification. So we do have a large number of attendees online today. So if you have any questions, you can just pop them into the chat question panel on the control panel on your screen, and then we'll answer those at the end. So Alex is going to help us out with reading some of the questions, Serkan. And we do usually get quite a lot of questions, so if we don't have time to answer your question live, we will make sure that we follow up with you via email. And of course, if you have any other questions following the webinar, you can reach out to us on our Ask TNav email here, or just send it over to me and I can pass it on to the right person. We are also recording the session, so that will be uploaded to our YouTube channel later today, along with the other two. So I will now hand you over to Serkan to start the presentation.
Thank you, Joanne, for that lovely introduction. As Joanne mentioned, the third part of our webinar series will deal with CCS, more from a reservoir engineering point of view, but also highlighting the different integrated technologies that we can actually offer related to that. Before I dive into some of the details, I would like to take a step back and look at the CCS questions on a higher level. So here I try to summarize them into three different areas. First one, you might call it the geological feasibility. So these are questions such as how much CO2 can we store, through what mechanisms, and the relative contribution of each mechanism. Second area, you might call operational feasibility. So here we're looking at what are the operational limits, safety limits, and any kind of possible constraints, such as maybe contractual ones. So this would deal with the surface network side of things, which my colleague in the previous webinar has gone into depth. Last but not least, you could talk about risk assessment. So things that might relate to leakage, migration, plume area, cross flow from abandoned wells, or formation integrity, which we will also have a look at in terms of geomechanics. After these three general areas that I've talked about, the three big CCS questions, I would like to basically spend the next 20 minutes or so trying to convince you that TNav is the answer to them. And before I do that, I would like to mention that our motto is one asset, one software. When we're working with tNavigator, we don't just work in silos. We don't have different types of models depending on which area we're looking at that we have to then pass back and forth. We can actually do all of the things that I put up on the screen in the same software. So that includes geological modeling, reservoir modeling, dynamic simulation, surface network modeling, PVT, well design, integration completion, and last but not least, uncertainty quantification, which we can actually look at all of these different areas as sources of uncertainty or ways of optimizing things. The tNavigator difference. So why should you use tNavigator instead of some of the other competitors? So the first feature is the set of advanced features that we actually offer within tNavigator, which is the broadest CCS-specific functionality in the market. We also offer a couple geomechanics without a separate license. So we are the only vendor that actually offers a fully implicit solution with geomechanics. So in general, when you work with geomechanics, you might know that you have a simulation grid and you have a geomechanical grid, and you need to couple them there are different ways of coupling them. However, we have a fully implicit coupling, which means that the user, from the point of view of the user, it's very easy to set up, and the full solution does not depend on any bottlenecks in the system where you might be waiting for the solution from one or the other simulator. We also offer integrated modeling, as I mentioned in the previous slide. So it's the only fully integrated solution from surface to subsurface, and a maximum simulation performance. So if you're at all aware of tNavigator's simulator and you've actually had a go at it, you would also agree with this, that we offer the fastest simulation on CPU and GPU. Depending on your hardware, you can utilize the best set of combinations of CUDA code and regular CPU code in C++. We also offer powerful Python methods, workflows where we already have preset items in our workflows that you can use to model anything you like, from static dynamic to uncertainty and optimization. However, if there's anything you'd like to modify or to fit your bespoke needs, we also offer fully integrated Python within tNavigator that you can actually write your own as well. Now, moving on to some carbon capture concepts. So the four listed here are the different trapping mechanisms. So those would be the structural trapping, residual trapping, dissolution, mineralization, and followed by geomechanics, which is equally important, and integrated network modeling, which I will also briefly touch upon at the end. So the CCS modeling capabilities, I mentioned the four trapping mechanisms. Here's a slide showing an example of maybe relative contribution from different trapping mechanisms, as well as how they are actually physically working. And after this short summary, I would actually like to go into each one separately. So structural trapping is the simplest one to understand, I suppose, where buoyant CO2 plume will actually migrate upwards within the reservoir until it meets an impermeable layer, such as a cap rock, or it could be any other low permeability layer. In this case, we have the structural trapping visualized at the end of CO2 injection here. And as you can see, there's quite a bit of it in different areas within the injection site. And this is the same picture after 100 years of injection, where you can see almost all the plume has actually migrated upwards into this structure here. An example that I'd like to use throughout the presentation is a small box model, where we will be progressively adding the different types of trapping mechanisms. Here you can only see the structural trap. On the left-hand side is the permeability of the model, with a high permeability reservoir part and a very low permeability cap rock part. And you can see the structural trapping, well, how CO2 plume actually looks like at the end of injection here on the right-hand side. The same picture now on the left-hand side in cross-section. And the question usually is what happens after 100 years, what happens after 1,000 years. Over here, we can see after 100 years that there is still some migration into this very low permeability layer, which we call the cap rock. And you can see that the plume actually stopped migrating where we have the artificial boundary at the end of the model, where the grid ends. And for situations like this, tNavigator offers many different ways of quickly reviewing your model, making quick changes, and adapting as new information comes in. So for example, we have structural uncertainty quantification, grid updating, manipulation, and extension, which normally might take considerable amounts of time and slow down your workflow. However, one example I'd like to highlight here is from the previous example where we said the plume actually meets the end of the grid and cannot artificially move further up anymore into shallower layers. We have a very simple item here which can actually extend the grid in all directions. The user can decide which direction or directions they'd like to extend the grid, whether it's just simple number of layers or to a given depth or to a horizon. In this case, what we've done is actually just increased it by 10 layers in the up direction. And we can then quickly populate the properties as well, all within a few clicks, and we can rerun the model to compare them what would happen if the grid were not artificially stopped here. So you can see the plume actually does not migrate much further than our initial case. So this is a very quick way of looking into your model in case you actually run into limitations that you did not plan for in the beginning. The next one I'd like to talk about is residual trapping. Here we have the CO2 being trapped through capillary pressure forces or hysteresis, basically different relative permeabilities we can supply. So in here is an example of a drainage and an imbibition curve. But we can also turn on the hysteresis option, which would then have several cycles of this. The example that I had from before is now on the left-hand side with only structural trapping after 100 years of injection. And on the right-hand side, we can see structural and residual trapping after 100 years of injection. And you can clearly see that the plume actually is retained, or more of the plume is retained within the injection site as compared to only structural trapping. In order to model residual trapping, one needs to be very familiar with relative permeability concepts, and to help the user and to make it user-friendly, we have a relative permeability designer, which is integrated into tNavigator. And here we can actually import our SCAL data from the lab directly. We can look at QC and match different data from the laboratory. We can also check different hysteresis models, as well as visualization of our final scaled or unscaled relative permeabilities. Just an example on that as well. Here's an example with no hysteresis, and here's one with hysteresis. The next trapping mechanism is solubility trapping. Here, CO2 will dissolve in other fluids, whether it's in a gaseous or supercritical phase. And as this happens, dissolved CO2 would make the fluid that it's dissolved in actually denser than the surrounding fluid. And as a result, the CO2-rich water would actually sink towards the bottom of the reservoir. So here we have, on the left-hand side, we have the solubility trapping at the end of injection. And on the right-hand side, we have after 100 years. So you can see the denser fluids will actually sink with time to the bottom, whereas initially they were actually behaving similar to the structural trapping situation we showed before. And we can actually model solubility in various ways. So we have a keyword called SoliHenry, which models solubility of CO2 according to Henry's law. You would have to use the gas sol keyword with SoliHenry. You can also use solubility and CO2 sol together, which would either take a default set of CO2 solubility, or user can actually supply this in a table, the solubility of CO2 in aqueous phase. And we have two other options here. Gas watt is only gas and water phase equilibrium model. So there are no other hydrocarbons here, there's no oil. And we have also the mutual solubility of CO2 and H2O, including salts, which is then the CO2 store option. And when we are looking at the gravity migration of CO2-rich solution, we have three different options to pick from. So this is basically what the density of the fluids would be like, or which correlation would be used to actually calculate the fluid densities based on the amount of CO2 dissolved in them. So the three options are Esroki's correlation, Garcia's correlation, Chen-Coates, and Nolan correlation as well, which the user can decide among the three. Speaking of solubility trapping, I'd like to also mention the PVT modeling capabilities, just very briefly. So we have different EOS models here, as you can see here in this list. And with time, we are adding more and more to these. The one we hope to add in the near future is also a free energy EOS, I guess more specifically GARE 2008. This will be very beneficial for CO2 applications. And as with many things with tNavigator, we actually rely on our on the cooperation between us, our developers, and also our users to actually improve the software and to make sure we can meet their demands. timely. On the right-hand side is a simple phase envelope. So within PVT designer package, we can actually do compositional black hole and thermal variants. Everything from importing your lab data, QCing, matching to different models, we can do within PVT designer. An example of a solubility trapping here. So on the left-hand side, again, our very first model with only structural trapping. In the middle, we have structural and residual trapping. And last but not least, on the right-hand side, we have the structural, residual, and solution trapping. And with solution trapping added, we can see that the plume actually migrates less aerially, but sinks more in the vertical direction. So again, more of the plume is actually retained around the injection site. If we look at 100 years post-injection of the two different methods of solubility, so on the left-hand side is Solubility and on the right-hand side is Henry or Soli-Henry, we can see that they're slightly different because the input data is different. However, what we can also notice is that they both stop at the bottom edge of the, they are impeded from moving further down. Similar to the previous example. So what we can also do is very easily extend the grid to the bottom so that we can actually see the full effect of what is happening due to the solubility of CO2. And here's a short video showing this as well. So the solubility trapping in effect. At first, you can actually see the plume migrating on the top of the reservoir. However, after a while, I will just repeat that. After a while, the solubility actually kicks in and you can see the denser fluid actually sinking to the bottom. And similar to this, I'd also like to show another model, this time highlighting the different visualization options within tNavigator. There are different panes here, a 3D pane, a 2D cross section, and we have the well section as well, the different properties actually in real time, all updating. Can also do cross plots. In this case, I've just put in solubility of CO2 in water versus mass density of water. And as you can see, as the plume migrates to the top of the reservoir, it actually also moves up dip here. Probably better seen in the cross section. And after some time, we have solubility trapping actually, the solution trapping actually manifesting itself. This is a short video from Model Designer, as I said, where you can actually integrate everything that is related, that is important for you, as well as offering many different ways of post-processing and QCing your data. The next trapping mechanism is mineralization trapping, where CO2 dissolves within the water and forms carbonic acid as a first step. However, a slower process that happens over longer periods is actually the carbonic acid reacting with salts in the solution or more likely in the surrounding rocks to form calcium carbonate, which then precipitates out of solution and can have effects on permeability as well as total porosity left for fluids migration. In case you have carbonate in the surrounding rocks, you would be forming calcium carbonate. If you have more magnesium, you might be forming magnesite. But there's different ways of doing this, and I will touch upon that in a second. But meanwhile, we can do chemical reactions either as where the components are part of the EOS or as part of a multi-component water option. In this example here, we can see the H2O and sodium chloride as components in the multi-component water option, which is very easy to set up using PVT Designer as well. Now, we talked briefly about reactions, and here I would like to also point out that we have a recent addition to Model Designer where we can actually deal with everything related to reactions in one window. If you are aware of setting up reactions with the traditional way, which is keywords, it's quite cumbersome because there are many keywords and it's not always clear from the order what is actually a reactant, what is a product, and balancing these equations is also not very easy. So we thought, why not make it easy for our users? Here you can see the reactants and products, and depending on the stoichiometry, you can actually put the numbers here as you need, and the reaction formula itself updates automatically. So you can also QC this very quickly. So in this window, we can supply information on reactants, products, reaction rate, activation energy, and many other parameters that you may need to set up for your reaction. Moving on from the trapping mechanisms, here I'd like to talk briefly about geomechanics. As I mentioned, we have a fully implicit solution where we can offer geomechanics free of cost on top of the simulator. Using geomechanics, we can look at caprock deformation, we can look at caprock failure, fractures within the reservoir, subsidence, basically any change of stress, strain, or well, as a result, also porosity within your reservoir will be reflected in real time in the model itself. So over here, we have an example of a roof deformation surface, which is exaggerated just to make the point here, where you can see subsidence in certain areas and elevation in other areas. Last but not least, I'd like to briefly mention integrated network modeling. So on the right-hand side, we have the fully implicit reservoir geomechanics coupling, which I just mentioned in the previous slide. Over here, we have the PVT designer, which is, again, all of these are integrated with each other. We have a well designer, which I haven't mentioned today, but if you'd like more on that, you can watch last week's webinar, where we can actually set up the well design the way that we would actually do in real life. So you have your casing, you have your tubing, packers, any kind of objects that you might want to model within your well design. And last but not least, the integrated surface modeling part can also be included so that we can actually look at long-term deliverability of CO2 to the reservoir. Over here, we might have a source, a sink, or actually directly connected to the well here. We might have a heating or heat exchange object as well. So as a short summary here, I would like to highlight that tNavigator can model all major CCS mechanisms. But this is not the only point here. We also offer the full suite of modeling capabilities in an integrated way. So everything from static modeling, dynamic simulation, geomechanics, well modeling, PVT modeling, service network modeling. And last but not least, all of these can have various parameters that can be variables, which can then be passed on to our history matching and uncertainty and optimization module to actually look at all the different scenarios in an automated way, making sure that there are no unforeseen situations that pop up during your project. So circling back to the very beginning of the presentation, I mentioned the 3 big CCS questions: the geological feasibility, the operational feasibility, and the risk assessment. And I would like to conclude with saying that the big CCS answer, in my opinion, is tNavigator. And with that, I'd like to end my presentation and look out for questions. Thank you very much for your time.
Thank you, Serkan. Yeah, I think we're going to pass over to Alex. So we do have a few questions coming through now. Can you see those, Alex?
Yes, absolutely.
Just while she's looking. As I mentioned earlier, we'll upload Serkan's presentation to our YouTube channel, and then you can see the other 2 presentations on there as well. And then obviously, if you have any other questions, then just get in touch with us. There is also a short survey after the webinar if you'd like to fill in and give us some feedback and suggestions for the future. Sorry, Alex, go ahead.
No problem, I'm ready. Thank you, Joanne. Thank you, Serkan. Thank you, everyone who put the questions in. We do have a few and not too many, so if you think of something else whilst we are here, don't hesitate to write in the box. We start with something positive. And generally, I'll be reading the question twice to give Serkan time to think. But first, we start with some comments. There's some comments saying that was a great presentation, Serkan. So well done, and thank you for the feedback. And now let's do the questions, the fun part. So the first question goes as follows, Serkan. From your experience, what tools in tNav are helpful during the project analysis? So from your experience, what tools in tNav are really helpful during the project analysis?
Thank you, whoever also gave the nice words there. I think for me, what I really value while I'm working on a project within tNav is the fact that everything is in one place. So I don't feel the need to export things or use external tools to do any kind of QC or whatever else that I need to do. If it's data manipulation, if it's post-processing or visualization or anything like that, I never have to go outside of tNavigator to do anything. And that for me is quite valuable. It saves a lot of time, and it also means visualizing certain things that you normally might not be able to put together using, let's say, several packages isn't the case. So I actually just use tNavigator to do that directly. Thank you for the question.
Thank you, Serkan. Okay, we're going to go to the next question. That one is a bit more detailed and tricky, so let's see how it goes. What percentage of CO2 is trapped by dissolution and sinking? How long does it take to see the sinking effect? What percentage of CO2 is trapped by dissolution and sinking? How long does it take to see the sinking effect?
Well, this is highly dependent on your model and your input parameters. I would say, if I had to rank them in general, I would say the plume kicks off first, and CO2 migrates upwards in the first place. So that's a relatively shorter process, whereas the solution can take a little bit longer. However, you can always tweak your model if you put in something that's unreasonable in terms of the solubility and the density models. Then you can also have that process working faster. But generally, it is slow compared to the initial injection of CO2 into the reservoir. The second question was how much of it, right? Again, would depend on your input parameters. So you have full control over what you can specify in terms of the physical processes happening. Sorry, I can't put a percent on that.
It's okay, thank you. Okay, we're going to go to the next one. This question is probably the one we anticipated because we discuss it amongst ourselves all the time. So here we go, Serkan. What would be the criteria to select one or the other, Solubility or Soluhenry? What would be the criteria to select one or the other, Solubility or Soluhenry?
Criteria in terms of results, I couldn't tell you. I mean, it would depend on a lot of things. However, they are different in the sense that using Solubility uses a different set of correlations, but also offers you the option to directly provide a table. So you can actually know at what conditions how much solubility of CO2 you want to allow in your model. So you have more direct control. If you don't put in it, if you just turn on solubility without the table itself, it will also take a default correlation. However, like I said, you have the option to actually explicitly state the amount of solubility going on. With Henry's law, it's a well-established law, and if you don't know anything from the lab, you might actually decide to go for that one because it's easier to set up. However, in terms of QCing or trying to figure out what is happening, how much solubility is going on based on what you put in, you would basically have to run the model and check it and then go back and change the parameters. So if you are kind of let's say the kind of person who wants to play around with things and figure it out, I think solubility might be better for you. you want to just leave it as is, Henry's law might be a better way to go. But yeah, unfortunately, there's nothing in terms of the for which type of projects you'd use which one. I don't have an answer for that. I don't think it exists actually.
Okay, thank you. There are actually more questions arriving. Let's see how many we will be able to answer right now. So the next one goes as follows. From the mechanisms presented, what mechanisms of CO2 trapping is the most challenging to model? So from these mechanisms presented, what is the most challenging to model?
I would say the most challenging to model is reactions. That's my personal opinion. I think because the others are relatively well understood, and I mean, so are reactions in theory. However, it's very, very hard to find some of the parameters that you have to put in, like reaction rates and so on. I mean, you know, if you're a geochemist and you've done this stuff before, or if you know where to look it up from, Freak-C or whatever, it's possible. But I find that this is the kind of the least understood part of it. So I often find models where people add CO2 with water, and then they have some solid coming out, which is just not the truth, but you basically take a shortcut because you don't know all the different parameters required for the full set of reactions that are actually happening. So yeah, I would say mineralization is probably the most challenging one.
Okay, thank you. So we have probably time for maybe one or two. It'll depend how difficult the questions are and how long the answers are, right, Serkan?
Yep.
So one next one is kind of looking at the practical aspect and the application. Have you used tNav for any projects that are actually ongoing, whether through EOR, onshore US, or through offshore projects like, not sure I can spell that correctly, Sleipner, Norway? So once again, have you used any of the projects, have you used tNav on any of the projects that are actually ongoing, whether through EOR or through offshore projects?
I guess have you doesn't refer to me personally, so I'm going to take it as, are they running projects? So I actually support a large client here in Germany, and they have ongoing projects with EOR since I started, basically the last 4 years, 5 years almost. However, that's not necessarily CCS related. More recently, obviously, as most people have felt it in the last year or so, the topic of CCS has exploded. So we've had projects in the North Sea. Maybe Alex can say more on that. We also have projects here, well, abroad, but for a German company here that we're working on. So yeah, that's my knowledge. Probably there's more going on in other geographies as well. Maybe Alex can add to that.
Yeah, to add to that, don't take it personally for sure, Serkan. And yes, we have a few ongoing projects that are CCS related. From my recollection, they are more for the capturing, not the EOR. However, there is a mix. We would probably need to check the global support as well to figure out how many projects in total are happening. What we're noticing for sure is a lot of demand. So whatever is ongoing now is going to probably be 3 or 5 times more in a couple of months by the look of it. So Joanne, what do you think? One more?
Yeah, one more.
One more. Okay, this is something that is another kind of expected questions, more generic one, I guess. Any advantages for modeling CCS using tNav compared to other commercial simulators available on the market? So Serkan, what do you think are the advantages of modeling CCS using tNav compared to other commercially available simulators on the market?
I mean, I kind of alluded to that in a previous question, I suppose. The very first one about the tools. So the set of tools that is integrated within the same software that you need to do CCS. In other places, you are distributed among different packages. So that's, I would say, integration is the biggest one. I would also add to that, because CCS is now quite a hot topic, and not every demand or not every let's say need from every user is currently met in the market, in terms of whether it's different physics or a combination of physics or anything like that. tNav is well placed, well positioned to actually develop these requests in a short amount of time. So those of you who are familiar with how we work, we actually have 4 major releases every year, and if any of you are clients, you would also know that from the time you requested something to actually seeing it in the new version might be 3 months, 6 months, even shorter, depending on what kind of request it is, which I don't know of any other vendor that does anything like this. So the alternative is waiting 1 or 2 years, and of course, the fact that we are also very fast in terms of simulation runtimes. So especially if you have a lack of lab data, or if you're not sure about your input data, what I'd like to do is actually give a range and just let AHM, the uncertainty package, give me a range of answers, and that helps me actually get a grip on what I'm looking at, rather than working with 1 or 2 cases. So I think those would be on my list, let's say.
Thank you very
Sounds like
much.
a nice way to end.
Yeah, that's a great opportunity to put Serkan on the spot. We do have a few questions that we received later than the others. So don't worry, we'll definitely come back through all of them and give you the answers.
Yeah, absolutely. As Alex said, we'll get those questions answered and emailed out to you. And yeah, thank you to everyone who's joined us over the last 3 weeks. Hope these webinars have been interesting and beneficial. And of course, if you do have follow-ups, maybe we can do a little bit of research internally and gather a few use cases and examples and stuff, and share that out with everyone. But of course, just contact us directly if you've got any specific questions, and we can certainly help you out. So thank you very much to everyone for attending, and to Serkan, Alex, and of course Mike, Alexei, and Maria, who have been helping us out over the last 2 weeks as well. And yeah, we look forward to seeing you again soon. Thank you very much.
Thank you very much. Have a nice day.
Thanks.
Bye-bye.
Bye.